Chances are you've heard about it more than once in your life, and even have your own ideas on the subject. But for space agencies around the world, futurists, and private aerospace companies, the idea of colonizing the moon is not a question of if, but when and how. For some, establishing a permanent human presence on the moon is a matter of destiny, while for others, it's a matter of survival. Over the past few decades, many plans have been dusted off and updated. So what would it take to establish a permanent human presence on the moon? When might it happen? And are we ready to take on this challenge? Let's go back in time to see what was proposed a few years ago. In 1959, the US military launched a study known as Project Horizon, a plan to establish a fort on the moon by 1967. The plan called for a first landing by 2 soldier astronauts in 1965, followed by construction workers and cargo delivered using iterations of the Saturn I rocket soon after. In 1961, the same year that President Kennedy announced the Apollo program, the US Air Force issued a secret report based on the US Army's earlier assessment of a military lunar base. Known as Project Lunex, the plan called for a lunar crew landing that would eventually lead to an underground Air Force base on the moon by 1968. In 1962, NASA published a study entitled Lunar Base. Their concept called for an underground base located at the Sea of Tranquility, the future landing site of the Apollo 11 mission. This base would rely on nuclear reactors for power and an algae-based air filtration system. The base would be composed of 30 habitat modules, divided into 7 living areas, 8 operations areas, and 15 logistics areas. The overall base would measure almost 140,000 square feet and could accommodate 21 crew members. During the 1960s, NASA produced multiple studies that called for the creation of habitats inspired by the mission architecture of the Apollo program. In particular, the Saturn V rocket and its derivatives. These plans called for the placement of space station modules on the lunar surface and the use of existing designs and technologies to reduce costs and ensure reliability. But perhaps the most influential design of the Apollo era was the 2-volume lunar base synthesis study completed in 1971 by the aerospace firm North American Rockwell. This study produced a design for a series of lunar surface bases, or LSBs. In recent years, several space agencies have written proposals for building colonies on the moon. In 2016, ESA proposed the creation of an international village on the moon as a successor to the International Space Station. The creation of this village would rely on the same interagency partnerships as the ISS, as well as partnerships between governments and private interests. Needless to say, the creation of a lunar colony would be a massive commitment of time, resources, and energy. While the development of reusable rockets and other measures reduce the cost of individual launches, sending payloads to the moon remains a very expensive undertaking, especially when several heavy launches would be required. There is also the issue of the many natural hazards of living on a body like the moon. These include extreme temperatures, where the sunny side experiences highs of 243 degrees Fahrenheit, while the dark side experiences lows of -45 degrees Fahrenheit. Most of the lunar surface is also exposed to meteoroid and micrometeoroid impacts. The moon also has an atmosphere that is tenuous. It is virtually empty. This is part of the reason why the moon goes through such extreme temperatures and why the surface is filled with impacts. It also means that all facilities will have to be airtight, pressurized, and isolated from the outside environment. The absence of an atmosphere as well as a magnetosphere also means that the surface is exposed to much more radiation than we're used to here on Earth. This includes solar radiation, which gets much worse during a solar event, and cosmic rays. Since the beginning of the space age, there have been multiple proposals for how and where a lunar colony could be built. The where is of particular importance, since any settlement will need to provide some degree of protection from the elements. As the saying goes, the 3 most important considerations in real estate are location, location, and location. For this reason, Multiple proposals have been made over the years to build lunar habitats in locations that would provide natural protection and/or containment. Currently, the most popular of these is the Aitken Basin at the South Pole, a massive impact region around the heavily cratered South Polar region of the Moon. One of the main attractions of this region is the fact that it is permanently shaded, which means that it experiences much more stable temperatures. In addition, several missions have confirmed the presence of water ice in the region, which could be harvested to make everything from hydrogen, from fuel to oxygen to drinking water and irrigation water. Beyond that, any attempt to colonize the Moon will have to take advantage of technologies like 3D printing, robots, etc. Bases will also need to be manufactured and supplied as much as possible using local resources. NASA and ESA have been exploring the concept for many years, and have both produced their own methods for turning lunar regolith and other resources into usable materials. For example, since 2013, ESA has been working to design the International Moon Village. Their proposed method of building this base involves placing inflatable frames on the surface that would then be covered with a form of concrete made from lunar regolith, magnesium oxide, and a binding salt. NASA has proposed a similar method that uses robotic workers using sintered regolith to print bases. This involves melting the regolith by bombarding it with microwaves, then printing it as molten ceramic. Other ideas involve building habitats in the ground and having an upper level that provides access to the surface by letting in natural light. There's even the proposal to build lunar colonies inside stable lava tubes. Another proposal is the solenoid moon base that would provide its own protection from radiation. This concept consists of transparent domes surrounded by a torus of high-voltage cables. This torus would provide active magnetic shielding against radiation and allow for the construction of colonies anywhere on the surface. The abundance of ice around the polar regions will provide settlers with a stable source of drinking water, irrigation, and could even be processed to produce fuel and breathable oxygen. A strict recycling regime will be necessary to ensure that waste is minimized, and composting toilets would most likely be used in place of flush toilets. These compost toilets would be combined with lunar regolith to create a growing soil, which could then be irrigated with locally harvested water. This would be essential, as lunar colonists would need to grow much of their own food to reduce the number of shipments that would need to be sent from Earth on a regular basis. Other energy sources could include solar arrays, which could be built around the edges of craters and deliver energy to the colonies there. Space solar power would also be able to provide abundant energy to colonies across the lunar landscape. Nuclear reactors are another option, as are fusion reactors. The latter option is especially attractive because helium-3, which is an energy source for fusion reactors, is more abundant on the lunar surface than on Earth. Mars. It's a pretty unforgiving place. On this dry and parched world, the average surface temperature is negative 67 degrees Fahrenheit, and at the poles, temperatures can reach negative 243 degrees Fahrenheit. This is largely due to its thin atmosphere, which is too thin to retain heat. So why is the idea of colonizing Mars so intriguing? Well, there are a number of reasons, which include the similarities between our two planets, the availability of water, the prospects of generating food, oxygen, and building materials on site. And there are even long-term benefits to using Mars as a source of raw materials and turning it into a habitable environment. NASA's proposed manned mission to Mars, expected to take place in the 2030s using the Orion Multi-Purpose Crew Vehicle, or MPCV, and the Space Launch System, or SLS, is not the only proposal to send humans to the Red Planet. In addition to other federal space agencies, there are also projects from private companies and non-private organizations, some of which are much more ambitious than just exploration. The European Space Agency has long-term plans to send humans, although it has not yet built a manned spacecraft. Roscosmos, the Russian Federal Space Agency, is also planning a manned mission to Mars, with simulations, called Mars 500, completed in Russia in 2011. ESA is also currently participating in these simulations. In 2014, NASA received its provisional support for Boeing's Affordable Mars mission design. Currently scheduled for the 2030s, the mission profile includes plans for radiation protection, centrifugal artificial gravity, in-transit consumable resupply, and a return lander. SpaceX and Tesla CEO Elon Musk has also announced plans to establish a colony on Mars, with a population of 80,000. Recently, Musk said that the first manned flight to Mars would take place maximum in the following decade, so we can expect to see the first Martian in the waters of 2030. There may come a day when, after generations of terraforming and many waves of settlers, Mars will also begin to have a viable economy. This could take the form of mineral deposits being discovered and then returned to Earth to be sold. But according to Musk, the most likely scenario, at least in the near future, would involve a real estate-based economy. With human populations exploding all over the Earth, a new destination that offers plenty of room to grow may look like a good investment. Once transportation issues are addressed, savvy investors will likely start buying land. Also, there will probably be a market for scientific research on Mars in the coming centuries. Who knows what we might find once planetary studies really start to open up? Over time, many of the difficulties of living on Mars could be overcome through the application of terraforming. There are many interesting similarities between Earth and Mars that make them a viable option for colonization. For starters, Mars and Earth have very similar day lengths. A Martian day is 24 hours and 39 minutes long, which means that plants and animals, not to mention human colonists, would find it familiar. Mars also has a very similar axial tilt to Earth, which means it has the same basic seasonal patterns as our planet, albeit with longer periods. Basically, when one hemisphere is pointed at the sun, it experiences summer, while the other experiences winter, with warmer temperatures and longer days. Also, like Earth, Mars exists within the habitable zone of our sun, aka the Goldilocks zone, although it is slightly towards its outer edge. Venus is also located in this zone, but its location is on the inner edge, combined with its thick atmosphere, has led it to become the hottest planet in the solar system. This, combined with its sulfuric acid rain, makes Mars a much more attractive option. In addition, Mars is closer to Earth than the other solar planets, with the exception of Venus. This would facilitate the colonization process. Indeed, every few years when Earth and Mars are in opposition, that is, when they are closest to each other, the distance varies, making certain launch windows ideal for sending settlers. In addition, Mars has vast reserves of water in the form of ice. Most of this water ice is located in the polar regions, but studies of Martian meteorites have suggested that much of it may also be locked up beneath the surface. This water could be extracted and purified for human consumption quite easily. Instead of bringing all their supplies from Earth, like the inhabitants of the International Space Station, future colonists could make their own air, water, and even fuel by splitting Martian water into oxygen and hydrogen. Preliminary experiments have shown that Mars soil could be turned into bricks to create protective structures, reducing the amount of material that needs to be transported to the surface. Terrestrial plants could also be grown in Martian soil, assuming they receive sufficient sunlight and carbon dioxide. But then, where on Mars will we start colonizing? Two main types of sites are getting attention as potential locations for colonization: caves in equatorial regions and lava tunnels. Mars Odyssey discovered what appeared to be the entrance to caves on Arsia Mons. It was hypothesized that colonists could benefit from the shelter that these caves or similar structures could offer against radiation and micrometeorites. Geothermal energy could also be present in the equatorial regions. Despite the advantages we have seen, colonizing the Red Planet also presents some rather monumental challenges. For starters, there's the issue of average surface temperature, which is anything but hospitable. While temperatures around the equator at noon can reach a balmy 68 degrees Fahrenheit, at the Curiosity site, Gale Crater, which is close to the equator, typical nighttime temperatures are as low as negative 94 degrees Fahrenheit. Gravity on Mars is also only about 40% of what we have on Earth, which would make adaptation quite difficult. According to a NASA report, the effects of weightlessness on the human body are significant, with a loss of up to 5% of muscle mass per week and 1% of bone density per month. Of course, these losses would be lower on the surface of Mars, where there is at least some gravity. But permanent colonists would still have to make extra efforts to overcome the problems of muscle degeneration and osteoporosis in the long term. And then there is the atmosphere, which is unbreathable. About 95% of the planet's atmosphere is carbon dioxide, which means that in addition to producing breathable air for their habitats, the colonists wouldn't be able to get out without a pressure suit and bottled oxygen either. Mars also lacks a global magnetic field comparable to Earth's geomagnetic field. Combined with a thin atmosphere, this means that a significant amount of ionizing radiation reaches the Martian surface. From measurements taken by the Mars Odyssey spacecraft, scientists have learned that radiation levels in orbit above Mars are 2.5 times higher than at the International Space Station. Surface levels would be lower, but still higher than what humans are used to. In short, the challenges to creating a permanent settlement on Mars are many, but not necessarily insurmountable. And if we decide as individuals and as a species that Mars should become a second home for humanity, we will undoubtedly find creative ways to address them all. Who knows? One day, perhaps even in our lifetime, there may be real Martians. Since humans began to look at the sky, they've been aware of the existence of Venus. In ancient times, it was known as both the morning star and the evening star because of its bright appearance in the sky at sunrise and sunset. Eventually, astronomers realized that it was in fact a planet, and that, like the Earth, it also revolved around the sun. And thanks to the space age and numerous missions to the planet, we learned what kind of environment Venus has. With a very dense atmosphere, making regular surface imaging impossible, heat so intense it can melt lead, and sulfuric acid showers, there seems to be little reason to go there. But as we've learned in recent years, Venus was once a very different place, with oceans and continents. And with the right technology, colonies could be built above the clouds, where they would be safe. So, what would it take to colonize Venus? As with other proposals to colonize the solar system, it all comes down to having the right methods and technologies, and most importantly, how much are we willing to spend? Most of the proposed methods for colonizing Venus focus on terraforming to make the planet habitable, but there are also suggestions on how humans could live on Venus without significantly altering the environment. Soviet scientists suggested that humans could colonize Venus's atmosphere rather than try to live on its hostile surface in the 1970s. More recently, a proposal suggested that cities could be built above the clouds of Venus. At an altitude of 31 miles above the surface, such cities would be safe from the harsh Venusian environment. The atmosphere of Venus is the most Earth-like environment in the solar system. In the short term, human exploration of Venus could take place from aerostat vehicles in the atmosphere, and that in the long term, permanent settlements could be realized in the form of cities designed to float at an altitude of about 31 miles in the Venus atmosphere. At an altitude of 31 miles above the surface, the environment has a pressure of about 100,000 pascals, which is slightly lower than that of Earth at sea level. Temperatures in these regions also range from 32 to 122 degrees Fahrenheit, and protection from cosmic radiation would be provided by the atmosphere above, with a shielding mass equivalent to that of the Earth. Venusian habitats would initially consist of aerostats filled with breathable air, a mixture of 21% oxygen and 79% nitrogen. These habitats are based on the fact that the air present in the balloons would allow them to float on the dense atmosphere of carbon dioxide. These would provide initial living spaces for colonists and could act as terraformers, gradually converting the atmosphere of Venus into something habitable so that the colonists could migrate to the surface. One way to do this would be to use these same cities as sunshades, allowing the atmosphere and thus the planet as a whole to be cooled little by little. This would work particularly well if the floating cities were made of low albedo materials. Alternatively, reflective balloons and/or reflective sheets of carbon nanotubes or graphene could be used. This offers the possibility of obtaining these resources using locally sourced carbon. NASA has begun exploring the possibility of mounting crewed missions to Venus as part of their High-Altitude Venus Concept of Operations, or HAVOC, which was proposed in 2015. The benefits of colonizing Venus are numerous. For starters, Venus is the closest planet to Earth, which means it would take less time and money to send missions there compared to other planets in the solar system. For example, the Venus Express probe took over 5 months to get from Earth to Venus, while the Mars Express probe took nearly 6 months to get from Earth to Mars. In addition, launch windows to Venus occur much more often, every 584 days when Earth and Venus are closest, compared to the 780 days when Earth and Mars are closest. Compared to a mission to Mars, a mission to Venus's atmosphere would also subject astronauts to less harmful radiation. This is partly due to the induced magnetosphere of Venus, which comes from the interaction of its thick atmosphere with the solar wind. Also, for floating colonies established in the atmosphere of Venus, there would be less risk of explosive decompression, since there would be no significant pressure difference between the interior and the exterior of the habitats. Thus, punctures would present a lesser risk and repairs would be easier to make. In addition, humans would not need pressure suits to venture outside, as they would on Mars or other planets. Although they would still need oxygen tanks and protection from acid rain when working outside their habitats, work crews would find the environment much more hospitable. Venus is also close in size and mass to Earth, resulting in a surface gravity that would be much easier to adapt to, 0.904 g. Compared to the gravity of the Moon, Mercury, or Mars, this would probably mean that the health effects associated with the weightlessness or microgravity would be negligible. In addition, a colony there would have access to abundant materials for growing food and manufacturing materials. Since the atmosphere of Venus is primarily carbon dioxide, nitrogen, and sulfur dioxide, these could be sequestered to create fertilizers and other chemical compounds. The CO2 could also be chemically separated to create oxygen gas, as the resulting carbon could be used to make graphene, carbon nanotubes, and other super materials. In addition to being used for potential solar shields, they could also be exported off-world as part of a local economy. Of course, colonizing a planet like Venus also comes with its share of challenges. For example, while floating colonies would be removed from the extreme heat and pressure of the surface, there would still be the danger posed by sulfuric acid rain. Thus, in addition to the need for protective shielding in the colony, the work crews and airships would also need protection. Second, water is virtually non-existent on Venus, and the composition of the atmosphere would not allow synthetic production. As a result, water would have to be transported to Venus until it could be produced there, i.e. bringing hydrogen gas to create water from the atmosphere, and extremely strict recycling protocols would have to be instituted. And of course, there's the issue of cost involved. Even with more frequent launch windows and a shorter transit time of about 5 months, it would still require a very heavy investment to transport all of the necessary materials, not to mention the robotic workers needed to assemble them to build even a single float. Yet, if we find ourselves in a position to do so, Venus could very well become the home of cloud cities, where carbon dioxide is processed and turned into super materials for export. And these cities could serve as the base for slowly introducing the Great Rain to Venus, finally becoming the kind of world that could truly live up to the name Earth's sister planet. Humanity has long dreamed of settling on other worlds, even before going into space. Contrary to one might think, the closest planet to our sun is in fact a potential candidate for colonization. While it experiences extreme temperatures, gravitating from heat that could instantly cook a human being to cold that could freeze flesh in seconds, Mercury is a potential target as a colony. A number of possibilities exist for a colony on Mercury, due to the nature of its rotation, orbit, composition, and geologic history. For example, Mercury's slow rotation period means that one side of the planet faces the sun for long periods of time, reaching maximum temperatures of 800 degrees Fahrenheit, while the opposite side experiences extreme cold of negative 315 degrees Fahrenheit. In addition, the planet's fast 88-day orbital period, combined with its 59-day sidereal rotation period, means that it takes about 176 Earth days for the sun to return to the same spot in the sky. So if a city were placed on the night side and had driving wheels so that it could keep moving to stay in front of the sun, people could live without fear of burning. In addition, Mercury's very low axial tilt means that its polar regions are permanently shaded and cold enough to contain water ice. In the northern region, several craters were observed by NASA's MESSENGER probe in 2012 that confirmed the existence of water ice and organic molecules. Scientists believe that Mercury's south pole could also contain ice, and say that about 100 billion to 1,000 billion tons of water ice could exist at both poles, which could be up to 20 meters thick in places. In these regions, a colony could be built using a process called paraterraforming. This concept consists of placing a pressurized enclosure that could be placed on the usable surface of a planet to create a self-sustaining atmosphere. Over time, the ecology within this dome could be modified to meet human needs. In the case of Mercury, this would include a breathable atmosphere, then melting ice to create water vapor and natural irrigation. Eventually, the region inside the dome would become a habitable habitat with its own water cycle and carbon cycle. Alternatively, water could be evaporated and oxygen gas created by subjecting it to solar radiation, a process known as photolysis. Another possibility would be to build underground. For years, NASA has toyed with the idea of building colonies in stable underground lava tubes known to exist on the moon, and geological data obtained by the MESSENGER probe during its flybys between 2008 and 2012 have led to the idea that stable lava tubes could also exist on Mercury. This includes information obtained during the probe's 2009 flyby of Mercury, which revealed that the planet was more geologically active in the past than previously thought. In addition, MESSENGER began spotting strange Swiss cheese-like features on the surface in 2011. These holes, known as hollows, could indicate that underground tubes already exist on Mercury. Colonies built inside stable lava tubes would be naturally protected from cosmic and solar radiation, extreme temperatures, and could be pressurized to create breathable atmospheres. In addition, at this depth, Mercury experiences much less temperature variation and would be warm enough to be habitable. At a glance, Mercury looks like the Moon. Its settlement would therefore rely on many of the same strategies as establishing a lunar base. It also has abundant minerals, which could help mankind with supplies. Like the Earth, it is a terrestrial planet, which means that it is composed of silicate rocks and metals that are differentiated between an iron core and a silicate crust and mantle. However, Mercury is composed of 70% metals, while the composition of the Earth is composed of 40%. Moreover, Mercury has a particularly large core of iron and nickel, which represents 42% of its volume. In comparison, the Earth's core represents only 17% of its volume. If mining could be done on Mercury, enough materials could be produced to provide mankind with an abundant resource on our present scale. Its proximity to the Sun also means that Mercury could harness an enormous amount of energy. This energy could be collected by orbiting solar panels, which would be able to harness the energy continuously and send it back to the surface. This energy could then be transmitted to other planets of the solar system with a series of transfer stations positioned at the Lagrange points. There is also the question of Mercury's gravity, which is 38% of Earth's gravity. This is more than double that of the Moon, which means that the colonists would have an easier time adapting to it. At the same time, the gravity is low enough to have advantages for exporting minerals, as ships leaving the surface would need less energy to get out of Mercury's pool. Finally, the Earth-Mercury distance is very interesting. Moreover, Mercury reaches the point where it is closest to Earth every 116 days, which is significantly shorter than that of Venus or Mars. Basically, missions to Mercury could be launched almost every 4 months, while launch windows to Venus and Mars should occur every 19 months and 26 months, respectively. In terms of travel time, several missions have been mounted to Mercury, which can give us a rough estimate of how long it might take. For example, the space probe to Mercury, NASA's Mariner 10, took about 147 days to get there. Of course, the ships used would be larger and would either take longer or use more advanced propulsion technology. Of course, a colony on Mercury would still be a huge challenge, both economically and technologically. The cost of establishing a colony anywhere on the planet would be enormous and would require shipping abundant materials from Earth or mining on site. In any case, such an operation would require a large fleet of spaceships capable of making the trip in a respectable amount of time. Such a fleet does not exist yet, and the cost of developing it, and the associated infrastructure to get all the necessary resources and supplies to Mercury, would be enormous. Relying on robots and in situ resource utilization, ISRU, would certainly reduce costs and reduce the amount of materials that would need to be shipped. But these robots and their operations would have to be protected from radiation and solar flares until they got the job done. And even after the colony is complete, the colonists themselves would have to deal with the ever-present dangers of radiation exposure, decompression, and extremes between heat and cold. As such, if a colony were to establish itself on Mercury, it would be heavily dependent on its technology. Moreover, until the colony becomes self-sufficient, those living there would be dependent on supply shipments that would have to come regularly from Earth. Once the necessary technology is developed and a cost-effective way to create one or more colonies on Mercury, these colonies could provide us with almost unlimited energy and minerals, along with a group of human neighbors called Hermians. Between the orbits of Mars and Jupiter lies the main asteroid belt of the solar system. In this region, it is estimated that there are more than 150 million objects. The largest of these is the dwarf planet Ceres, the only body in the main belt large enough, 584 miles in diameter, to have undergone hydrostatic equilibrium, become spherical. Because of its interesting location and the amenities this dwarf planet possesses, some have proposed that we establish a colony on Ceres. This could serve as a base for asteroid mining ventures as well as an outpost for human civilization, which could facilitate human expansion further into the solar system. But could a colony really exist on the icy surface of Ceres, and what would it take to create and maintain such a colony? Colonizing Ceres would use a number of the same methods used to establish colonies on the Moon, Mercury, and the satellites of Jupiter and Saturn. Basically, the idea is to establish structures optimized for bodies that have little or no atmosphere and are subject to extreme temperatures, i.e. pressurized, airtight, and highly insulated infrastructures. These could be established in impact craters, which would then be sealed with the attachment of a dome. Regolith extracted from the asteroid belt could then be used to 3D print a base layer next to the ice and then print structures. The ice and organic molecules could be harvested locally to provide water and nutrients that, combined with the regolith, would provide the soil needed to grow food. Alternatively, a colony could be established in the icy crust of the planet. This would be very beneficial if engineers were to attempt to speed up Ceres' rotation, although this is a major challenge in and of itself. With the vertical axis of the colonies pointing toward the center of Ceres, this rotation would generate a centrifugal force that would provide artificial gravity. With the local availability of water ice, minerals, silica, and other raw materials, some degree of self-sufficiency could be achieved over time. Already, the fact that Ceres is the largest body in the asteroid belt makes it a good location for a potential colony. It could serve as a main base and transportation hub for asteroid mining, allowing resources mined from the belt to be transported to Mars and/or Earth. It could also be a stopover and refueling point for missions to the outer solar system. This means that it would take much less thruster and energy to launch a spacecraft from its surface than with other solar system bodies. Transportation to and from Ceres with other planets would therefore be much cheaper and more energy efficient. Ceres' rich resource base also makes it an attractive property. The availability of water ice, for example, means that a colony could be largely self-sufficient, with colonists able to provide their own oxygen as well as drinking water and irrigation. The presence of methane and ammonia could also be used to make fuel, nitrogen gas, or exported to help terraform planets like Mars and Venus. The presence of these resources also means that a colony could be built using the resources harvested there. The resources from Ceres and the surrounding belt would also mean that the colony would not need to import resources from Earth and/or other places outside the belt. Although it is the largest body in the main asteroid belt, Ceres is considerably smaller and less massive than most solar system objects. With a diameter of 584 miles, Ceres is about half the size of the Moon. But because Ceres is largely composed of water ice and less dense material, it is only 1% of the Moon's mass. This results in a very low surface gravity of about 3% of Earth's. This would result in people living on the surface of Ceres being in a near weightless state all the time. As a result, they would experience physiological effects very similar to those experienced by astronauts during long-term stays on the ISS. These include muscle loss, loss of bone density, diminished vision, decreased organ function, cardiovascular problems, and even psychological effects. For this reason, medical treatments or some form of artificial gravity, centrifuges or increased rotation for example, would be needed to ensure that the colonists did not have to limit their time on Ceres. And of course, there's a considerable expense that colonizing this body would entail. While the necessary resources could be harvested locally, ships capable of long-duration deep space missions would be needed before missions could be considered. This would likely involve nuclear thermal or nuclear electric propulsion concepts, or perhaps something more advanced. It is also likely that any attempt to establish a permanent base in the main asteroid belt would have to wait until infrastructure was first built on the Moon, Mars, and everywhere in between. Any attempt to colonize the main asteroid belt would otherwise be prohibitively expensive and would likely collapse before future missions could reach and resupply it. But as time passes and colonies are established closer to Earth, a colony on Ceres would be the next logical step. Not only would this open up the main asteroid belt to economic exploitation, but it would also serve as a stepping stone to the outer solar system, which could lead to the establishment of colonies on the moons of Jupiter and beyond. Since the Pioneer and Voyager probes passed through the system decades ago, scientists have suspected that moons like Europa could be our best bet for finding life in our solar system beyond Earth. And because of the presence of water ice, interior oceans, minerals, and organic molecules, it's been speculated that humanity might one day establish colonies on one or more of these worlds. Since the Voyager probes passed through the Jovian system, several proposals have been made for crewed missions to Jupiter's moon, and even the establishment of colonies. For example, in 1994, the private spaceflight company known as Project Artemis was created with the goal of colonizing the moon in the 21st century. But in 1997, they also developed plans to colonize Europa, which included the establishment of igloos on the surface. These would serve as a base for scientists who would then dig into the moon's ice crust to explore the underground ocean. This plan also discussed the possible use of air pockets in the ice cap for long-term human habitation. In 2003, NASA produced a study called HOPE that focused on the future exploration of the solar system. Because of its distance from Jupiter and therefore low radiation exposure, the target destination for this study was the moon Callisto. The plan foresaw the beginning of operations in 2045. These would begin with the creation of a base on Callisto, where science teams could remotely operate a robotic submarine that would be used to explore Europa's inner ocean. These science teams would also dig surface samples near their landing site on Callisto. Finally, the Callisto expedition would establish a reusable surface habitat where water ice could be harvested and converted into rocket fuel. This base could then serve as a refueling base for all future operating missions in the Jovian system. Also, in 2003, NASA reported that a manned mission to Callisto might be possible in the 2040s. This mission would rely on a ship equipped with a nuclear electric propulsion and artificial gravity, which would carry a crew for a 5-year mission to Callisto and establish a base. There has also been the proposition of exploitation of the atmosphere of the outer planets, including Jupiter, to obtain helium-3 fuel. A base on one or more of the Galilean moons would be necessary for this. NASA has also speculated about this, explaining that it would provide unlimited supplies of fuel for fusion reactors here on Earth and anywhere else in the solar system where colonies exist. Establishing colonies on Galilean moons has many potential benefits for humanity. For one thing, the Jovian system is incredibly rich in terms of volatile compounds, which include water, carbon dioxide, and ammonia ice, as well as organic molecules. In addition, Jupiter's moons are also thought to contain massive amounts of liquid water. Colonies on Jupiter's moons could enable missions to Jupiter itself, where hydrogen and helium-3 could be harvested as nuclear fuel. Colonies established on Europa and Ganymede would also allow for multiple exploration missions to be mounted in the inner oceans that these moons would have. Since these oceans are also considered some of the most likely locations for extraterrestrial life in our solar system, the ability to examine them closely would be a boon to scientific research. Colonies on the moons of Io, Europa, Ganymede, and Callisto would also facilitate missions further out into the solar system. These colonies could serve as staging points and refueling bases for missions to and from Saturn where additional resources could be harvested. In short, colonies in the Jovian system would provide humanity with access to abundant resources and immense research opportunities. Of course, these challenges are large in size and numerous in number. They include, but are not limited to, radiation, long-term effects of lower gravity, transportation issues, lack of infrastructure, and, of course, the total cost involved. Given the danger of radiation to exploration, it is appropriate to address this aspect first. Io and Europa, being the closest Galileans to Jupiter, received the most radiation of all these moons. This is compounded by the fact that neither has a protective magnetic field and very tenuous atmospheres. As such, the surface of Io receives an average of about 3,600 rems per day, while Europa receives about 540 rems per day. Ganymede is the only Galilean moon, and the only giant non-gas body other than the Earth, to have a magnetosphere. However, it is still controlled by Jupiter's powerful magnetic field. On average, the moon receives about 8 rads of radiation per day, which is equivalent to what the surface of Mars is exposed to in an average year. Only Callisto is far enough away from Jupiter that it is not dominated by its magnetic environment. Here, radiation levels only reach about 0.01 rems per day, just a fraction of what we are exposed to here on Earth. However, its distance from Jupiter means that it also has a fair share of problems, not the least of which is the lack of tidal heating in its interior. Another major problem is the long-term effects that the weaker gravity on these moons would have on human health. On the Galilean moons, the surface gravity varies from 0.126 g for Callisto to 0.183 g for Io. This is comparable to the Moon, 0.16 g, but much less than Mars, 0.37 g. And while the effects of low G are not well understood, it is known that the long-term effect of microgravity includes loss of bone density and muscle degeneration. Compared to other potential colonization sites, the Jovian system is also very distant from Earth. As such, transporting the crews and all the heavy equipment needed to build a colony would take a long time. To give you an idea of how long it would take, let's consider a few actual missions to Jupiter. The first spacecraft to travel from Earth to Jupiter was NASA's Pioneer 10, which was launched on March 3, 1972, and reached the Jupiter system on December 3, 1973, a flight time of 640 days. Pioneer 11 made the trip in 606 days, but like its predecessor, it only crossed the system on its way to the outer planets. Similarly, the Voyager 1 and 2 probes, which also passed through the system, took 546 days and 688 days respectively. Juno, meanwhile, was launched from Earth on August 5, 2011, and reached its orbit around Jupiter on July 5, 2016, a travel time of 1,796 days, or just under 5 years. And it should be noted, these were unmanned missions, involving only a robotic probe and not a ship large enough to accommodate large crews, supplies, and heavy equipment. As a result, colony ships would have to be much larger and heavier, and would require advanced propulsion systems, such as nuclear thermal or nuclear electric engines, to ensure that they made the trip in a reasonable amount of time. Missions to and from the Jovian moons would also require bases between Earth and Jupiter to allow for resupply and refueling, and to reduce the cost of individual missions. This would mean that permanent outposts would have to be established on the Moon, Mars, and most likely in the asteroid belt before any missions to Jupiter's moons would be considered feasible or cost-effective. These last two challenges raise the question of cost. Between building ships capable of making the trip to Jupiter in enough time, establishing the necessary bases to support them, and the cost of establishing the colonies themselves, colonizing the Jovian moons would be incredibly expensive. Combined with the risk of doing so, one must wonder if it's even worth it. On the other hand, in the context of space exploration and colonization, the idea of establishing permanent outposts on Jupiter's moons makes sense. Any challenge can be met, provided the proper precautions are taken and the right resources are committed. And while we have to wait for the similar colonies to be established on the Moon and Mars, it's not a bad idea as far as next steps are concerned. With colonies on one of the Galilean moons, humanity will have a foothold in the outer solar system, a stopover for future missions to Saturn and beyond, and access to abundant resources. What we know about this system has increased dramatically in recent decades, thanks to missions like Voyager and Cassini. With this knowledge have come multiple proposals on how Saturn's moons should one day be colonized. In addition to being the only body other than the Earth to have a dense, nitrogen-rich atmosphere, the system also holds abundant resources that could be exploited. Just as the idea of colonizing the Moon, Mars, the moons of Jupiter, and other bodies in the solar system, the idea of establishing colonies on the moons of Saturn has been widely explored in science fiction. At the same time, scientific proposals have been made that outline how colonies would benefit humanity, allowing us to mount missions deeper into space and ushering in an era of abundance. Colonization of the outer solar system includes mining the atmosphere of these planets and establishing colonies on their moons. In addition to Uranus and Neptune, Saturn has been identified as one of the largest sources of deuterium and helium-3, which could stimulate the ongoing fusion economy. Titan is a prime candidate for colonization because it is the only moon in the solar system to have a dense atmosphere rich in carbon compounds. On March 9, 2006, NASA's Cassini spacecraft found possible evidence of liquid water on Enceladus, which was confirmed by NASA in 2014. According to data derived from the probe, the water emerges from jets around the south pole of Enceladus, and this water is only tens of meters below the surface in some places. This would make collecting water considerably easier than on a moon like Europa, where the ice cap is several kilometers thick. The data obtained by Cassini also indicated the presence of volatile and organic molecules, and Enceladus also has a higher density than most of Saturn's moons, indicating that it has a larger average silicate core. All of these resources would be very useful for building a colony and providing basic operations. Compared to other places in the solar system, such as the Jovian systems, Saturn's larger moons are exposed to considerably less radiation. For example, Jupiter's moon Io, Ganymede, and Europa are all subject to intense radiation from Jupiter's magnetic field, ranging from 3,600 to 8 rems per day. This amount of exposure would be lethal, or at least very dangerous, to humans, requiring extensive countermeasures to be put in place. Of Saturn's larger moons, Mimas and Enceladus are in this belt, while Dione, Rhea, and Iapetus all have orbits that place them just outside Saturn's radiation belts. In addition, the frozen volatiles and methane harvested from Saturn's moons could be used to terraform other places in the solar system. Colonies on Saturn's moons could also serve as bases for harvesting deuterium and helium-3 from Saturn's atmosphere. The abundant sources of water ice on these moons could also be used to make rocket fuel, thus serving as staging and refueling points. In this way, a colonization of the Saturn system could fuel Earth's economy and facilitate exploration further out into the outer solar system. Of course, colonizing Saturn's moons poses many challenges. These include the distance involved, the resources and infrastructure needed, and the natural hazards that colonies on these moons would face. For starters, while Saturn may be abundant in resources and closer to Earth than Uranus or Neptune, it's still very far away. On average, Saturn is about 8.5 astronomical units from Earth. To put this in perspective, it took the Voyager 1 probe about 38 months to reach the Saturn system from Earth. For crewed spacecraft carrying colonists and all the equipment needed to colonize the surface, it would take much longer to get there. These ships, in order to avoid being too large,